What makes nuclear weapons tick? And more specifically, what aspect of the atom is being exploited in harnessing nuclear weapons? After all, if all matter contains atoms, why can't you use any material to make an atom bomb? What's so special about uranium? We're going to be covering the answers to these questions and more in today's video. This is the second part of a two-part series where we go through all of the essential details and what went into making an atom bomb. In the first video, we already covered the basic structure of an atom and differentiated between terms such as atomic number, atomic mass, mass number, and isotopes. So if you missed that video or have a ChatGPT level of understanding of those concepts, I recommend watching part 1 first, which I've linked in the description below. And at the end of part 1, I left off with a question. What keeps all of the positively charged protons together in the tight confines of an atom's nucleus? Or at least stay together long enough to prevent something like Turns out there's a third force at play here, which is much stronger than the repulsive electrostatic force, at least at small distances. This force is known as the strong nuclear force, and attractively acts between protons and neutrons, which are collectively referred to as nucleons. Although, unlike gravity and electrostatics, the nuclear force only acts strongly at very tiny distances, and exponentially decreases in strength beyond 2.5 femtometers. And at too close a distance, such as those shorter than 0.7 femtometers, this force becomes highly repulsive. So it is this force that is entirely responsible for the small size and shape of atomic nuclei. You can think of forming an atom like pushing a ball up a hill. And then at the other side, there's a large valley. When protons are free from the confines of an atomic nucleus, they are repulsed by their mutual electrostatic force. That is, bringing two protons in proximity requires energy for overcoming their like-charge repulsion. However, if enough energy is provided to get the protons close enough, that is, within range of the strong nuclear force, the protons feel an enormous attraction. This attraction brings the protons together until they hit the strong repulsion of the nuclear force around 0.7 femtometers. In fact, when considering the work required in overcoming the electrostatic repulsion versus the work performed by the strong nuclear force, there's actually a surplus of energy in bringing the protons together. Put another way, the two-proton system is in a more stable energy configuration than when the two protons were free particles. The excess in energy is released as heat energy after the atom is formed, and this reaction is referred to as a fusion reaction. Keep this in mind for the next part. Now, once an atom is formed, there's something fishy that happens to its mass. It's rather subtle, but we'll see it loud and clear in an example. I also left this as an open question from the last video, but if you didn't get a chance to work through the numbers, it's okay. We'll work through it now. And if you didn't get a chance to subscribe last time, now's a great time to consider subscribing to my channel and hitting that like button. Okay, so now, let's see what this looks like in the uranium isotope U-235. U-235 has an atomic number of 92, so it has 92 protons and 92 electrons. Subtracting 92 from its mass number of 235 brings its number of neutrons to 143. Now, multiplying the individual masses of each proton, neutron, and electron by their respective numbers within the U-235 atom, we find the total mass to be 236.966 AMU. But the mass, as measured by mass spectrometry, and as listed on the periodic table, is 235.0439 AMU. This is a difference in mass of almost 2 AMU, or almost 1%. What's going on here? It turns out this isn't a fluke, and isn't just unique to U-235. It stumped the scientific community until Einstein's theory of special relativity, published in 1905. The Mass Equivalence Principle was a direct consequence of special relativity, and you all know it as E = mc². From this equation, all mass in the universe is equivalent to a store of intrinsic energy. The amount of energy available to potentially be converted is equal to the mass m times the speed of light c squared. Since the speed of light is such a huge number, this implies that even very small masses contain enormous amounts of energy. So how does this relate to atomic nuclei? Remember when I mentioned that the fusion of two protons into an atomic nucleus released its excess energy as heat? A good question to ask is, how is this energy accounted for? Well, according to relativity, it's in the mass, or rather, the lack of mass. Essentially, the energy released by forming an atomic nucleus is accounted for by a reduction of mass in the nucleus. And this is why an atom's total mass is less than the sum of its parts. This mass difference is known as the mass defect of an atom. So, the missing mass difference we found earlier in U-235 is the mass defect. Now, if we take that mass defect and apply Einstein's equation, E equals mc squared, we'll find a corresponding energy. This energy is referred to as the binding energy of the nucleus. This is essentially the energy you would need to supply in order to break apart the nucleus into each of its constituent particles. The higher the binding energy, the more stable the nucleus. For U-235, the binding energy equates to 2.86 times 10 to the minus 10 joules. This is a small amount of energy, and usually when discussing atomic size energy scales, an alternative unit of energy is used, known as the electron volt, or EV for short. 1 EV is the amount of energy it takes to accelerate 1 electron through a potential difference of 1 volt. In units of EV, the binding energy of U-235 computes to 1.785 billion electron volts, or 1.785 GeV. This binding energy is not unique to uranium. Because of the strong nuclear force, every atomic nucleus with 2 or more nucleons has a binding energy. However, the binding energy of each element is not the same. In fact, it's these differences in binding energies that will be exploited by nuclear weapons. But before we dive into that, let's gain some intuition for binding energy. Let's consider 2 different sized nuclei. A small nucleus on the left and a large nucleus on the right. You can imagine the forces acting within a nucleus will vary depending on both the nucleon number as well as the overall size of the atomic nucleus. Remember, the nuclear force only acts effectively at distances within 2.5 femtometers. So for the larger nucleus, the nucleons around its outer perimeter will feel an overall smaller nuclear force than those within the interior. The repulsive electrostatic interaction will also become more significant with the larger nucleus, since it contains more protons. Both effects, taken together, will erode away at the binding energy of the large nucleus. This is precisely why the more massive elements experience a higher likelihood of instability. In order to make a fair apples-to-apples comparison between the binding energies of all of the elements, it's useful to normalize an element's total binding energy by its corresponding number of nucleons, or its mass number A. So in our example of U-235, we can divide 1.785 GeV by 235 to arrive at a binding energy per nucleon of 7.59 MeV per nucleon. This is the number that is commonly listed on a detailed periodic table and helps make a fair comparison between each element's binding energy. Let's see what this looks like and find some trends. To start, let's plot the binding energy per nucleon as a function of atomic mass number. And since isotopes of neighboring elements often share the same mass number, we'll focus on the average value for each mass number, which will be highlighted in red on our plot. So if you read the plot from left to right, an increase in mass number implies more nucleons are added to the nucleus. More nucleons implies that the strong force increases, and hence the binding energy of the nucleus also increases. At least, this is what our intuition would suggest. However, this trend only continues until peaking at 8.8 MeV, or around a mass number of 56, corresponding to iron. Past this point, the nucleus has become large enough where the nuclear forces are unable to extend across the entire nuclear diameter. The electrostatic repulsive forces between the protons have also increased and begin to reduce the energy savings provided by the atomic nucleus. Notice, this is the regime where our U-235 isotope lives. Given the instabilities that arise with higher mass number elements, Many of these elements give rise to a phenomenon known as radioactive decay. Radioactivity was first experimentally discovered in 1896 by Henri Becquerel and Marie Curie. They observed radioactivity in both uranium and thorium, well before any of the theory we just discussed was understood. Radioactive decay is a process where an unstable atomic nucleus emits energetic particles, and in the process of doing so, changes its elemental type. For instance, over time, the unstable U-235 nucleus is known to decay into thorium-231 by emitting a highly charged helium nucleus. In a decay equation, the mass numbers of each element are indicated by superscripts to the left of their atomic symbol, and the atomic numbers are indicated by subscripts. Notice, the atomic numbers and mass numbers on both sides of the reaction must balance. The highly charged helium nucleus in this reaction is known as an alpha particle, and this particular radioactive decay is known as alpha decay. This is one example of many of the various decays possible in radioactive materials. Radioactive decay is statistical in nature, and the probability of its occurrence is governed by quantum mechanics. So although it's impossible to predict its occurrence for a single atom, large groups of atoms of the same element behave in a very predictable way. For instance, a pure bar of U-235 will lose half of its atoms to alpha decay every 700 million years. In nuclear physics, this time is referred to as the half-life, which is essentially the amount of time it takes for half of a radioactive isotope to decay into another element. However, this process can be sped up. One method of artificially inducing a nuclear decay process is known as neutron capture. In this process, a free neutron is directed towards an atomic nucleus, and the nucleus absorbs the neutron, or, as the name suggests, captures it. This effectively increases the mass number of the isotope by 1. For elements with mass numbers greater than 56, or that of iron, adding a neutron effectively lowers the binding energy of the nucleus. Remember, the binding energy is the energy holding the nucleus together and contributing to the stability of the atomic nucleus. If the binding energy of an already unstable nucleus gets lowered even further by neutron capture, then this can cause the unstable nucleus to split into two. The process of an atom splitting into two less massive nuclei is known as fission. In addition to two nuclei, a fission reaction can also release additional particles in the process. Let's see how this looks like for our U-235 atom. When a neutron is captured by a U-235 nucleus, there are actually several known possible fission reactions that can occur. In each possible fission reaction, the uranium nucleus splits into two nuclei of approximately the same mass. For the sake of illustration, let's just consider uranium's fission into barium-141 and krypton-92. In this reaction, the number of protons and neutrons on the left-hand side equates with the total number of protons and neutrons on the right-hand side. Notice that this fission reaction releases two additional neutrons in addition to the original free neutron. Now, let's see what happens when we total the mass for each side of the equation. For the left-hand side, we can look up the mass of U-235 as well as the mass of a free neutron. This brings the total mass of the left-hand side to 236.0526 AMU. Now for the products. We can look up the mass of barium-141 and krypton-92 on the periodic table. And after totaling, we find the total mass of the products to be 235.8666 AMU. This is a difference of 0.186033 AMU, or just below 0.1% of the original U-235 nucleus and free neutron. This is weird, right? Each side of the equation has the same number of protons and neutrons. Where did the mass go? Well, remember the plot of the binding energy versus mass number from before. The binding energy of U-235 is much less than the binding energy of its fissile products of barium and krypton. And also remember, the higher the binding energy, the greater the mass defect. So the missing mass on the right-hand side of the equation is due to the higher binding energy per nucleon of both barium and krypton. Now, it makes sense why the masses may be different, but again, energy must be conserved. This means the gains in binding energy are accompanied by a release in energy equivalent to the missing mass. We can find this amount of energy using Einstein's equation, or the energy released is equal to delta M times C squared. This brings the energy released from a single U-235 fission reaction to 173 MeV. So a fission reaction is essentially a conversion of binding energy and releases any energy gains as a form of heat energy. In isolation, the energy released from a single fission reaction is benign and isn't enough energy to be concerned about. But that's only the energy released from one atom. Fission becomes concerning when the neutron byproducts of one fission reaction generate additional fission reactions in neighboring atoms. And then the byproducts of those reactions continue additional fission reactions, and so on. This is known as a nuclear chain reaction and is at the heart of any nuclear fission bomb. Keep in mind, however, there's a lot of engineering that must go into crafting such a sustainable fission chain reaction, and this was largely what had to be developed during the Manhattan Project. The first challenge is elemental purity. Obviously, if you have a block of material that's not over 90% of the radioactive isotope, then the ejected neutrons will simply be captured by the non-radioactive atoms within the material, and the chain reaction will not sustain itself. Obtaining pure radioactive isotopes is easier said than done because, well, by their very nature, they're unstable and hence not commonly found on Earth. Remember, the radioactive isotope U-235 is only found in 0.72% of all uranium samples on Earth. Separation of U-235 from the much more common isotope of U-238 is also challenging. Both isotopes have the same electron configuration, so chemical separation is not possible. And the negligible atomic mass difference between these isotopes makes standard mass separation techniques also challenging. This challenge of purifying enough pure U-235 during the Manhattan Project was taken on by the lab in Oak Ridge, Tennessee. Once you're able to purify a radioactive isotope, the question becomes, how much of it is needed? Most depictions of nuclear chain reactions almost suggest the neutrons ejected from a fission reaction are conveniently aligned along each row of atomic nuclei and instigate successful fission reactions in each row of neighboring atoms. The real picture isn't quite so nice and tidy. Remember earlier when I mentioned matter is mostly empty space? Atomic nuclei only occupy very small fractions of an entire material's volume. And the ejected neutrons from a fission reaction, they can be ejected in any random direction. This means an ejected neutron must travel a relatively long distance before encountering another nucleus primed for fission. This distance is known as the mean free path, since its statistical nature. And the fissile material must be at least this distance in all three dimensions to sustain a nuclear chain reaction. If the pure material is not wide enough, the neutrons will simply be ejected from the material and not generate subsequent fission reactions. To ensure the smallest physical dimensions, the fissile material is typically formed as a sphere that has a radius large enough to support the mean free path of neutrons ejected from subsequent fissile reactions. The mass of such a sphere is often cited as the critical mass required for a fission chain reaction. For U-235, this mass is around 52 kilograms, and the sphere has a diameter of just over 17 centimeters. The sphere of critical mass is often surrounded by a neutron reflector to enhance the reactivity and direct emitted neutrons back towards the fissile material. To initiate the nuclear chain reaction, a neutron source is placed within the vicinity of the fissile material, and the neutron source is activated when the bomb is detonated. Immediately after the first neutron is fired, the first fission reaction initiates the nuclear chain reaction, and the metal enclosure of the fissile material is designed to withstand an internal pressure of 80 generations of the chain reaction. The average kinetic energy of the neutrons released from each fission reaction is around 2 MeV, which brings their average speed to around 6.5% of the speed of light. With a sphere of U-235 having a diameter of around 17 centimeters, this implies each generation of fission takes place every 8.7 nanoseconds. And in 80 generations, the entire chain reaction of the fission bomb is completed in just under 1 microsecond. And then, the energy released is substantial. 80 generations of chain reactions, with each generation doubling the previous, implies 2 to the 79 fission reactions occurred, or 6.04 times 10 to the 23 fission reactions, with each reaction releasing at least 170 MeV of energy in the process. This brings the entire theoretical energy yield of a U-235 fission bomb to at least 1.6 times 10 to the 13 joules. To put the power of an atomic weapon into perspective, let's do a quick comparison to something we're all familiar with. Remember that Discovery rocket ship discussed from a previous video? Its max power output during a launch is 37 million horsepower, or 27.2 gigawatts. The fission bomb generates as much power as 870 million rocket ships. President Roosevelt authorized the Manhattan Project on December 28, 1942. This project was as much of a material science problem as it was a nuclear physics problem. At the time, it was unclear if enough pure U-235 could be produced for the necessary critical mass. So, in addition to U-235 purification, the project also concentrated efforts on creating a plutonium bomb, with plutonium-239 being another unstable radioactive isotope, and could be created via neutron capture of the more common U-238. Most of the plutonium production for the project occurred at the Hanford Engineer Works in Hanford, Washington. By the end of the summer of 1945, the Manhattan Project successfully had obtained enough U-235 and plutonium-239 to construct 3 bombs. On July 16, 1945, the Trinity test was the first successful detonation of a nuclear weapon using a fission chain reaction of plutonium-239. Only 24 days after the Trinity test, a U-235 bomb nicknamed Little Boy was dropped on Hiroshima. 3 days later, a plutonium bomb nicknamed Fat Man was dropped on Nagasaki. 6 days after the second bomb was dropped, the Japanese surrendered to the Allies, and the official Japanese instrument of surrender was signed on September 2, 1945, bringing the official end to World War II. Spies during the Manhattan Project fed secrets to Communist Russia, which opened the path for Russia's nuclear development. Only 4 years after the Manhattan Project, Russia successfully tested their first nuclear bomb, First Lightning, on August 29, 1949. This spurred the United States to develop an even more powerful fusion bomb, led by Ed Teller. To get a quick sense for the energy released by a fusion bomb, refer to the chart of the binding energy again. Our original fission bombs capitalize on the binding energy gains going from right to left in a fission reaction. Fusion bombs, on the other hand, capitalize on the energy gains of fusion reactions going from left to right, which are much more substantial in energy. Since they bring atoms together, fusion bombs require some initiation energy. Because of this, fusion bombs have 2 stages. The first stage is a fission bomb, which applies the energy requirement of fusion. The second stage uses this energy to initiate a fusion reaction between atoms of liquid hydrogen. The first successful detonation of a fusion bomb was on the island of Elugelab on November 1st, 1952, which, upon detonation, completely wiped the island off the face of the planet. Over the years since, the number of active nuclear weapons exponentially increased between the world's superpowers. This number peaked at the height of the Cold War in 1986, with an estimate of over 60,000 nuclear weapons worldwide. Since the end of the Cold War, nuclear disarmament has become more of a priority, but at present, there are still an estimated active total of over 9,000 nuclear warheads stockpiled across 10 countries around the world. There are countless avenues and rabbit holes to go down when discussing nuclear weapons and the persistent challenges they pose on society today. But I'll close with this. In 1947, the Doomsday Clock was created by the Bulletin of Atomic Scientists, an organization founded by Albert Einstein with Robert Oppenheimer as its first chair. The clock's minute and second hands serve as a visual symbol for how close our world is to a human-made, global catastrophic event, with Doomsday symbolically set for occurring exactly at midnight. Each year, a select group of globally recognized scientists and leaders adjust the clock's hands, depending on current threats to humanity from unchecked scientific and technological advances. The original Atomic Commission set the clock's hands to 7 minutes to midnight, considering the advent of nuclear power and the bombings of Nagasaki and Hiroshima. But since its inception, the clock's hands have been adjusted accordingly. For instance, in 1991, after the Cold War, the clock's hands were actually set back to 17 minutes to midnight after the apparent end of the Cold War and the fall of the Soviet Union. However, as history has unfolded, this position was short-lived. Throughout the clock's 76-year history, the closest the atomic clock has ever been to midnight was set in January of this year, 2023, at which its current position is 90 seconds to midnight. Indeed, the legacy of Oppenheimer and the Manhattan Project is one we must never forget. Thanks for watching. This is Dr. John.